Hello, can you hear me? Shyam, can you hear me?
Yes, sir, I can hear you, but the voice is very low. Sound is very low, I think. I think it's because of my internet.
Just a minute, okay. So now you people can hear.
Yes, I can hear you, sir.
Okay, so Zanfar is here
Yes,
today.
sir.
Yes, sir.
I'm glad to see you. You don't appear usually. So, Amna said your mic is okay today.
Yes, sir.
Good. Zanfar, I will kick you out. You didn't submit the assignment.
Sir, I will submit before the deadline.
But why are you
Actually,
waiting?
I'm busy. Sir, I'm doing some research work, that's why.
Mhm. Okay. So, okay, so 1, 2, 3, 4, 5. Okay, so it's 5 people here. Okay, so slowly people are reducing. Okay, so what we are studying in the last class, anybody can remind me?
Sir, we were discussing the properties of laser.
Yeah.
It is monochromatic and the temporal and spatial coherence and the directional properties.
Okay. Okay. So, I mean, the properties, I think 1 or 2 things are left. So, okay. So, one of the property of the laser is brightness. So, brightness, if you have seen the laser, I mean, you must have observed the brightness of the laser. And if the light is not bright enough, sometime monochromatic lights, they are bright, but not that much bright as compared to the laser. So you can see here some of the GIFs here, that animated stuff, that the brightness of the laser, which is one of the properties. And we need to know how to calculate the brightness. So brightness, basically, you can see the formula here, the simple formula. That is power over beam diameter and beam divergence. So first we need to know the beam divergence, which we studied in the last lecture. And when you are studying the beam divergence, then at that time you can also measure the beam diameter. Okay. And power, you can have a power meter or something like this. And with the help of this formula, you can find out the brightness. So this is your formula for the brightness. And there are some complicated equations are also involved, but I'm not going in that kind of detail. There's too much physics of these kind of things. So here, this is a very practical kind of formula which is engineers, I mean, they use when they work with the laser. Okay, so now I can see the Aksa is also here. Welcome, Aksa. Okay, so brightness, and after that, very important thing, intensity. How intense laser is. So basically, what intensity tell you that how much power is concentrated in a given area. And if the beam is very intense, like the pinpoint focusing, like it's not occupying much area, then maybe it's more intense. But if it is occupying the more area, maybe it will be less intense. So, it's formula to find out the intensity here. You can see that P over area spread. This is the simplest formula, okay? There can be complicated stuff. But what I'm showing you, I mean, like usually the technologists or these people, they use. So the power and area spread by, you know, that R square, R is the radius. So what this formula is showing, that if area actually is inversely proportional and power is directly proportional here. Okay, so if the spot size is bigger, the intensity drops. Okay, you can see in this animation as well here, if you can observe, when the beam area is increased, you can see it become less intense. Okay, and power, we take it in watts, and radius in meters. Okay, and actually this is a cross section of the beam spot here. Usually this kind of thing, if we like in the lab or something like this, we use a CCD camera. So CCD camera basically is used to find out the cross-sectional area of the beam, what is the size of the beam, the spot size. And the unit for the intensity here, you can see that it's a power per unit area. Okay, so still there are some things in the properties. Irradiance is very important as well, and irradiance and intensity, somehow it's confusing, and sometimes they are same. Like here, you can see this formula here, E is equal to P over A. Same thing like in case of intensity, the power over area. Okay, and if you see here, this is a GIF, I mean, and you can see the beam is falling and the rust is removed. But you can see the shiny portion here when the beam moves. And how much irradiance we need to perform this kind of action. Okay, how much intense light has to be. So we use this formula to find out the power, how much power we can have, and what is the area on which we are going to shine the laser to remove the rust. Okay, And this brightest portion, this is actually is the highest irradiance power per unit area. It's the most intense area. Okay, so now move further. If we compare light bulb with the laser and the radiance or intensity of the light bulb and the radiance and intensity of the laser. So on the left side, what you see, you know that the light spreads in all the directions when it comes out from the simple light bulb. And in case of laser, it doesn't spread. Okay. So what do you see here? And on the left side here, this portion, the light spread in all the directions, first thing, and second thing, distance from the light bulb. We assume 1 meter. Okay. We go 1 meter away from the light, and we can see that what we want to measure, intensity or irradiance, you can say. So what will be intensity after 1 meter from the source? And we use a formula here. Okay. And what we get here, that 0.796 Weber per meter square. Okay. Forget the unit at the moment. Watt per meter square. Okay, if just forget it and see the comparison just here. In this case, the light here, you have 79.6. Okay, so clear difference here. And what it shows that the laser light is more intense. Okay, and here you can see the beam radius, the distance is 1 meter, and laser power is just 1 milliwatt here. Okay, and here is a 10-watt bulb. Okay. One more thing actually, which I will not tell you, but you have to figure it out by yourself. That here in this formula, 4 is used, but not here. Okay, so that you have to figure it out. Okay, so now we finish the properties, and we will move towards energy states. Okay. Okay, so you know that, I mean, all of you studied physics, basic physics, and there are some in the atom, there are energy levels, low energy level and higher energy levels. And we assume that the electrons are jumping from one energy level to another energy level. Okay. So I will not go to that much detail of atomic physics, but a little bit which is related to the laser, and when we study the laser, so we need to know these kind of things. So transition between the energy states. First thing is absorption. What is absorption? One photon is coming, and electron, it made the electron from the lower energy level to jump to the higher energy level. Okay, and it absorbs. So this is simply, I mean, we can say it's absorption. Okay, and what is absorption? for your reference, is written here. It's absorb the energy and jump from lower energy level to higher energy level. Here, this is wrong actually. This has to be 1. Okay, this is wrong. This is 2. So, and you can see here how it is animated. Second option or second case, spontaneous emission, which is happening in a natural way. And without spontaneous emission, we cannot have a laser. Actually, we cannot have a stimulated emission. So, this spontaneous emission, you can see here also mentioned in the wrong order. So this is E1 and this is E2 and this is E1. So what do you see here? That it is happening that electron is decayed, or atom is decayed actually, more correct way. And electron jump or move from the higher energy level to the lower energy level, E2, E1. And it may release a photon. This kind of phenomena is happening, and this release of photon, because if many photons are released in this way, they may not be coherent to each other. Okay, so this is a pretty random process. And what is the difference of energy? You people already know here, E2 minus E1, and Planck's constant and frequency. Okay, so absorption happen by some way. Electron jump from energy level 1 to energy level 2 or any other higher level, and then randomly spontaneous emission happen that the electron can go back to their lower level and release some photon which is not coherent. So third case, stimulated emission. Stimulated emission, so here is also by mistake, so it has to be E2 and it has to be E1. Okay, so this is not correct. Okay, so what is happening here? As you know, all of you probably, that stimulated emission is very important. And stimulated emission, without stimulating, we cannot have a laser. And to have a stimulated emission, we need to have a spontaneous emission. And spontaneous emission is always there. So in the beginning, usually, when we start the laser, if you have worked with a laser or something like this, you can clearly observe that when the laser is started for a few seconds, something like this, you can see the incoherent light. That is because of the spontaneous emission. And slowly, it becomes coherent because stimulated emission overcomes the spontaneous one. Okay, so similar kind of formula here. And what we do here, the electron is in a higher state, like here. Okay, and we introduce a photon, a burst of photon, single photon, and it made this electron to decay to lower energy state. Okay, so in this case, it emits the photons. So these photons are coming and making it to happen, it's stimulating it, And in this way, this process is started and many photons are released. And these photons are released in phase and coherent. We have same polarization. There are long theoretical explanation of this with the very long equations, but which is not a scope of this book. Sorry, this course here. So stimulated emission, one photon stimulate the other photons, stimulate the electron and jump to lower level or state, and other photons are released, and all these photons are in phase with each other and have the same polarization. So this is the stimulated emission in simple words. Okay, so these were about the energy levels. So basic processes of laser action, actually, what we need to have is population inversion. What is population inversion? You can clearly see here in this figure. So we need to have a population inversion and we need to have a stimulated emission. Okay. So in case of a normal distribution, the lower energy level or the lowest energy level, it's highly populated. Okay, so electron mostly stay there. And then higher, and then the highest one, it's not populated. So if the ground state or the lower state is populated, but higher states are not populated, it means even though we stimulate, we cannot have a laser. Okay. So I must say, I should not say in this way, because stimulation will only happen when the population inversion is there. Okay. Because it makes the electron to fall from higher to the lower level. That is when we stimulate. Okay. And also stimulation help to have a population inversion. What is population inversion? That higher levels highly populated, more electron on the higher levels. Okay. So ground state less populated, or the low state, and high state are more supposed to be more populated, which is not a normal phenomena actually. In the normal state, or in the normal case actually, not state, the lowest energy level or energy state is always highly populated. So we need something. So we supply energy from outside to make this thing possible, have population inversion, and then to lasing to happen. Okay, so what do you see here? This is a similar kind of thing which I have shown you before. Here, if you see in this kind of animation, the electron highly populated area is the lowest one. Okay, and here if you see, population inversion happen, and what we have, more electrons in the higher state. Okay, so I don't get excited here. And we supply the energy from outside, and this is how things are stimulated, and we have photon at the output. These animation are showing like this. Okay, so basic thing in these slides to know or to understand the population inversion. And population inversion can only happen if you have a pump and supply energy from outside. So population inversion only exists if you apply something from outside, stimulated light, a coherent light, or incoherent light as well. Okay. So now these are Boltzmann, this is actually the Boltzmann equation. Thermal equilibrium, you must have heard about this one. I don't want to go in much detail. When I will upload this lecture, the PDF, you can go through and you can read. This equation is important to tell about the population of the energy levels. Okay. And it very much depends on the temperature here. So the temperature, increase the temperature, and what will happen? We'll show you in the next slide here. So in this animation, what you see that you can observe the temperature is changing here. Okay. And this equation also called, that Boltzmann distribution or something like this. So lower the temperature, the lower level more occupied, and if the temperature is increased, it excited more. This animation is not 100% correct. I mean, it's some idea it will give you. Okay. So, and the temperature is in the Kelvin, and this one, that Boltzmann's constant and energy. And in normal case, that it's distributed in a different energy levels. Ground level or lowest level are highly occupied or populated. Okay. And because there is always some thermal energy at temperature above 0 K, always some thermal energy. And because of this thermal energy, the electrons you can find in higher energy levels sometimes. Okay. If we take the ratio, take two energy levels here, E1, E2. Okay. And temperature is there. So this is the ratio. This ratio will tell us which level is more populated, which one is not. So if the ratio is level equal to 1, then both levels are same, something like this, roughly. So as I mentioned that N2 is a population in the upper state and N1 is population in lower state. Okay. In the thermal equilibrium, that okay, in a thermal equilibrium, we assume that N1 and N2 are equally populated, or N1 is greater than N2. Even N1 equal to N2 is not very much possible. N1 is greater than N2. This is the normal case. Okay. So lower level is highly populated. This is, you can see here. And that is thermal equilibrium. I mean, the electron are jumping to up and come down. I'm jumping up and come down. The level is almost same, or N1 is greater than N2. But it's not happening like to have N2 greater than N1. So if N2 greater than N1, that will be a population inversion case. Okay. Laser cannot be operated when there is a condition of thermal equilibrium. So we have to break this condition. So how we break? We use the pump source. We use the pump and that stimulate. Okay. And this is one of the example. I mean, you can go through and you can see I put some values here. At the room temperature here, these are the energy levels, and these are the temperature 300 K. And what is the value of this ratio? Okay. And what is the value of this ratio here? So at room temperature is 0, but in case of if the temperature is raised, its value is 0. Okay. I will not go in this detail. You people go through and see. I may give you the assignment related to this kind of thing or homework later on. Okay, this is just a high school kind of thing. Okay, and this sentence is important here. It's thermal equilibrium. More atoms are in the lower energy state than in the higher energy state, or equal, which is the extreme case. So it's a normal distribution. So we have to break this distribution to have lasing action. Okay, how many people are present here? Please write yes in the WhatsApp group. Okay, so I want to know that how many people. So this will be kind of attendance. Okay. Okay, so this is also related to the relative population, and you can see two possibilities. Whether to change the energy of the energy levels and whether to change the temperature, and observe what ratio we see of this Boltzmann distribution. Okay. So if the energy level are close to each other or the temperature is very high. So what does it mean? That here, if the energy level are very close to each other, then it means the difference between the E2 and E1 is approximately 0. And if the temperature is very high, it's infinite, in both the cases, situation will be same. N2 is equal to N1. Okay. So this is a limit. I mean, if the energy levels are very close to each other or temperature is very high, the same ratio it will come. So as long as the material in the thermal equilibrium, the higher state population cannot exceed the population of the lower state. Okay. So what this graph is showing here, you people are already aware of this kind of graph. So what it shows, the temperature and a relative population, N1 over N2. Sorry, N2 over N1. Okay, so temperature is increasing and ratio is also increasing. Okay, and what happened actually? It approaches to 1 approximately, but never exceed it. This is the ratio is 1 approximately. Okay, but never exceed. We want this thing to happen. Okay, so for this thing we need population inversion and stimulation. So under steady state condition, what I explained, like energy absorption, spontaneous emission, and stimulated emission, it happens simultaneously. Okay, simultaneously, not separate processes. It's a simultaneous process. Like here, you can see here absorbing, here spontaneous emission and stimulated emission, and we have laser action. Okay. Einstein's coefficients. What are the Einstein's coefficients? Three possibility: absorption, spontaneous emission, and stimulated emission. Okay. So here is absorption, spontaneous, and stimulated emission here. Okay. So absorption case we can call B12, and in case of spontaneous, electron is coming from up to down, A21, and in case of stimulated emission, we are forcing electron to jump from up to down, so we call it B21. In case of absorption, what is happening from energy level 1 to energy level 2, so 1, 2. Okay. So if we substitute and make an equation like this, what this thing is showing, that something externally is involved. This one is radiation. This is a pumping source. This is for the stimulation. Okay, we introduce in this one because in case of absorption, photon coming from outside. Okay, and in case of stimulated emission, the photon is also introduced. So that is why we introduce here this radiation. In case of spontaneous, we don't need to have this kind of thing. Okay, but these processes are interlinked with each other. Okay, so equation can be written like this. Okay, these are simple things which you can see, and with the help of these equations, you can understand somehow this absorption, spontaneous emission, and stimulated emission, and you can solve further to get some more mathematical relations, which I'm not teaching you here. So these coefficients, basically it's predicted by the Einstein's called the Einstein coefficients. Okay, so condition for the amplification. This is not that amplification yet. This is amplification in the gain medium when the photons are multiplying. Okay, 1 photon, 2, 3, 4, 5, 6. So you call it condition for light amplification. In any case, this amplification is also happening because number of photon in the gain medium is increasing. Okay, and what you see here is the ratio between the stimulated to spontaneous emission. Okay, and this is the ratio between stimulated emission to the absorption. Okay, in both the cases, this radiation source is involved, so at the end you get N2 minus N2 by N1. Okay, if we say, or if we assume that B21 and B12, you go back, this is a B12 in case of absorption, and this is B21 in the case of stimulated emission. If B21 and B12 are equal to each other, because in both the cases radiation is coming from outside. Okay, and then in this case, the probability of stimulated emission transition is equal to the probability of stimulated absorption transition. Okay, like here, this will be cancelled out. And what you get, simple, N2 over N1. Okay, so this is one of the things that you need to understand. What these equations are telling, why these equations are important to know. Okay, if we move further, this is also condition for the amplification. This ratio, we know that stimulated to spontaneous emission Okay, and this one from the previous slide, we know that when B21 is equal to B12. Okay, and for the stimulated emission, it's not for the stimulated. Stimulated emission causes this thing actually. N2 greater than N1 population, and the higher level is more than the population in the first level. Okay, so if as long as we have N1 greater than N2, the option is dominating. Okay, not the stimulation emission. Randomly photons are absorbed. Okay, not a systematic way. So we cannot stimulate in this case. Okay, so absorption has to overcome with a very, like intense burst of light or something like this, used as a pump stimulate. Okay, so if this condition is existing, then population inversion happens. And population inversion happens, then it means this process will be continue. Pumping is going on. We are stimulating continuously so that the photons are increasing in numbers in the gain medium. Okay, so this is how it's amplifying. Okay. And it depends how much you pump and how long, for how long time you pump. Okay. Okay, so let's move to the next slide here. When we study the energy states, in a simple case, we need something which we call the metastable state, where the electrons can stay for a longer time. Okay. So it can stay for the longer time, and it's called the metastable state. Metastable state is not naturally existing actually. The dopant, you know that in the case of a laser material, always we use the two materials in simple words. Doping. Okay. And that dopant causes this metastable, which is very important for the lasing. Maybe in the next slide you will see. So what is happening? The excited state, it has a shorter time, usually 10 to minus 9 seconds. So it means that it's a short time, it immediately drop down. Okay. We need some extra levels where the electron can stay. Okay, so that is metastable state. And metastable state, their decay time is usually higher than the excited state. Okay, and it can be in a picocycle or something like this. So relatively long-lived states are called the metastable states. It's not temporarily generated states, but it's metastable states. When we use the dopant, then it happens. And this metastable state, it helps to have a population inversion. Okay, in the diagram, the later one, maybe you can understand more. So in case of ND-YAG, I'm giving you the example. This is solid state laser. So ND-YAG, ND, neodymium, is a dopant. Okay, and the YAG, yttrium aluminium garnet, is a host. Okay, so Okay, so I just looking, I mean, how many people are coming and going. Okay, so I think this lecture will be extended to the extend a little bit more. Okay, so I will share the link. Okay, so this is the neodymium is a dopant. Okay, and the YAG is a yttrium aluminium carbonate is a host. Okay. If you simply use a YAG, there will not be a laser. The ND, when ND is introduced, is a dopant. It's a very small quantity. It causes the metastable level, and then we have a lasing. Okay. Similarly, this is ND YAG, and there is a laser of which is ND glass. Okay. So ND glass is a host, ND is dopant. Okay. So this is how same. I mean, like ND is here is a dopant, so it will help to have a metastable level. Okay. And then if you have metastable level, then you have a population inversion. Okay. Now, laser also classified in another way, which we call 3-level laser or 4-level laser. In actual materials or the gain medium, the levels are not like so simple. We can just use the lines to interpret somehow. Okay. Here, this is, I just drew some lines. I call this one is excited level. This one is ground level, lower level, and this one is intermediate level between these two levels. It's called metastable level, metastable state. And this one is generated in 3-level system. This is a 3-level system now. Okay. I will tell you later which one is the category of 3-level laser and 4-level lasers. Not in detail, but a little bit. On the right side, this is a 4-level laser. So whatever the material use, 4 levels. Okay. So this one is the metastable state, lower state, ground state, and excited state. So the atom stays here for a while, for longer, because it has a longer decay time. It doesn't let the electron fall down until the beam comes from outside to make it. Okay. So this is a 4-level system. This is a 3-level system. Okay. And one of the level, whether it's 3-level or 4-level, one of the level is supposed to be metastable level. And that is because of the dopant. Okay. Now, if we move further, what do you see here? 3-state or 3-level system. Okay. Here, this is the diagram of 3-level or 3-state system. What is happening here? This is your ground state. Okay. And from the ground, electron, or in general terms book, we say atom. Okay. I'm saying electron. We pump. Okay. And this pumping causes the electron from a lower state to jump to the higher state, top state, which is also called the pump state actually. And because of this energy level, here it's also called the absorption band. It's not necessary to call it absorption band, but the pump band we can call it. When the electrons reach here, then because of the shorter decay time, it moves towards the lower level, which is a metastable level. Okay. So metastable level here, it stays. Its electrons from lower level to higher level it's going and coming down to stay at a metastable level. So in this way, this metastable level is highly populated. It becomes highly populated as compared to the ground. Okay. And then we have, and then when it's accumulated here, the electron, then it moves down to the ground and it emits the photons, which is a laser action in phase coherent. This is 3-level system. On the right side here, this pattern is showing you very somehow in an interesting way. This is your ground level here, okay, and ground level is because electrons are jumping from up to the excited level, okay, and this is not N2 actually, E3 something. When it now here we have less and here we have more, and when the electron from this level is going down, so metastable level is populating, okay, and when the metastable level is going down here, you can see the photons are coming out. This is the laser action. This is somehow relative animation so that you people to understand, not exactly 100%. Okay, so showing the population. So metastable level, more electrons staying at the metastable level, and finally, when it decays, the electrons move to the ground state, then you will have a laser action. 3-level system mostly, it's hard to operate in 3-level lasers. It's hard to operate in a continuous mode. Usually they are pulse lasers and longer pulse lasers. Because for the CW, it is because in this case you apply the energy and you need to apply very high energy. And this is like this. And now 4th level. If you go to the 4th level, okay, let me, I end this session here and I will send you the link because the recording is going on. It takes some time to finish. And within 5 minutes, you people can rejoin. Okay, so I am ending now and I'm rejoining after 3-4 minutes. Okay, don't go away, stay.